Bismillah ar-Rahman ar-Rahim. Welcome. In the first session, inshallah, about maybe a series, I will call it mathematical physics. And today we'll discuss linear algebra, and specifically we'll discuss the linear algebra in the context of quantum mechanics. So this is all the linear algebra you need before you go and study quantum mechanics in more depth. So in general, the objective of this is to study essentially the part of linear algebra that is related to quantum mechanics or needed for quantum mechanics. Now, whenever you study a branch of mathematics, it's important first, before you start, to identify two things. The first are the objective that we are dealing in this branch of mathematics, and the second is the relation between these objects, which sometimes called arrows. So basically, all branches of mathematics that you can think about it are just to answer these two questions. What are these objects that we are dealing, and what's the relation between these objects? For example, you study calculus, right? In calculus, you study the object. We can think about them as intervals, the real line intervals, and the relation between them are function. So a function, you have a function that sends an interval to another interval, okay? In topology, you have the open set, and the relation between them are what's called the homeomorphism, and etc. So in the linear algebra, we have the thing that we study are the objects, which are the vector spaces, and the relation between these two vector spaces are linear maps. So we can, in summary, define linear algebra as the studying the objects, which are called vector spaces, and we study the relation between them, which are identified by linear maps or linear transformation or linear operator. So the topics of this session, which may be divided into 3 videos or more or less, will be focusing in the first part will study the vector spaces. We'll know the properties of this object, and we will cover everything, all the needed theorem on them. After that, we will move in the linear maps or linear transformation, and that's it. We are done with linear algebra. So what's a vector space? So we start first with the objects. So the vector spaces are a vector space V. From now on, I will denote V to be a vector space. So even if I don't say so, it's known to be a vector space over a field K, or K is a set. Of course, I will identify what do mean. Is a set of elements which called the vectors. So basically, a vector, which is V, the large V, you have something alpha, beta, is a set of anything. These things, we call them vector. They are satisfying some condition. What are these conditions? First, if you sum two vectors, this means belongs to. So if you sum two vectors, you will get another vector in the set. So for example, V, if you have alpha, beta, gamma, if you sum alpha and beta, you must get gamma or alpha or beta again. Let's assume this only the set. So it's closed under addition. If you add 2, you will still be in the set. Another, if you multiply it by scalar, the vector, you multiply it by a scalar, you will get again you will be in the set, the same set. For example, if we have V is alpha, beta, gamma, the same, and I multiply alpha by 5 alpha must be also in the set V. Okay. Now K is what? K basically is the set of scalar. To simplify the thing, K could be the complex numbers or could be the real numbers. These are the only two possibilities that we're dealing with. So K, so we said we have vector space over K. What does that mean? That means the scalar that I multiply with the vector is brought from the set K. Okay, as it's written here, K usually is C, the set of the complex numbers, or K is the set of real number. So now we have what's called the such close under addition and close under scalar multiplication. We call this a scalar multiplication, and we call this addition of two vectors. Now, simple examples. We have the R. So R3 is that we know, which consists of vectors like this: alpha, beta, gamma, where alpha, beta, and gamma are real. So these are real numbers. And over R, so that means the scalar that I multiplied is a real number. We have the same thing, R3, but we can just use a complex scalar. So for example, we have this vector 1 0 0, and we can multiply it by I, so it's a vector space. Actually it's, oh yeah, this is wrong, it should be C. Why is that? Because if I have 1 0 0, this is a vector space. The first, it's a vector space. The second is not a vector space, because if I have 1 0 0 and I multiply it, I get I 0 0, which is not in R3, but it is in R and C3. In general, we'll have Cn. Cn is a vector which consists of n elements. Let me call it A1 up to An, and all these A's, R, and C. This kind of vector space is very important, because usually we'll deal in quantum mechanics. In quantum mechanics, we'll see, or we'll deal only with two vector spaces. This is the vector space over C again, so we can multiply it by any complex number, where alpha is a complex also. So this is a very important and crucial vector space that we will deal with. And the second is this vector space, which is, we denote it as C. C here stands for continuous. So, and we put like an interval. So that means this is the set of all continuous function for the interval A and B. So this is a vector space. So this is the whole notation for the vector space over C. Again, that means that we can multiply it by a scalar from the complex numbers. Is the set of all continuous function from, continuous function on, there is none. So on the closed interval AB. For example, you can have a function like sine x. Any function, you have the continuous function, the constant function, etc. So all these are elements which belongs to the CAB, or the continuous function, and then on AB. Now in the quantum mechanics, we have a special notation. So we will deal with most of the cases, as I said, we'll deal with the continuous function. I will call it just continuous function for just any sake of time. And we'll deal with Cn over C. So these are the two vector spaces that most likely we'll deal with in quantum mechanics and in general in physics. And the second thing is that a vector will be denoted as this notation, which is called Dirac notation, because it was introduced by Dirac. This actually, we call it a kit, and we will see why we call it a kit. But this vector, لما يكون على اليمين, so it is on this triangle on the right, we call it kit. So let me write it. It is kit. So basically, a vector denoted as a kit. So we will have the previous property that if you have two vectors or two kits, you will get a vector again. And if we multiply a kit by a scalar, we will get a vector. Now, a linear combination, maybe most likely you are familiar with this terminology. Linear combination of a vector. So if I have, as I said, I will use the kit notation. So if we have k vectors, so v1 up to vk, a linear combination is basically you multiply each one by a scalar and you sum. So from the name, it's a linear combination. Now a span is a set. So if I have a span of k vectors, so this is the notation, we call it a span of this vectors, is basically is the set of all possible linear combination. So now I'm not fixing this constant, but rather I'm changing them. I'm taking all the possibility. So this is called the span. It's the set of all possible linear combination. So we write it mathematically like this. So I take these are the linear combination, and we are varying, or we are taking all the possibility of these constant. Now we define the notion of linearly independent. So what do we mean by when we say a set of vectors are linearly independent? Basically, if we equate the linear combination to be 0, so we have this linear combination is equal to 0. This is only if each scalar is 0. So maybe this is up to k. So maybe this is not clear for you, and I will explain what's the notion behind it. Let me assume that one of these alpha is not 0. For simplicity, I will take specific value. Let me assume that alpha 3 is not equal to 0. So what I will do, this means alpha 3 from this equation, V3 is equals to what? Is equals to alpha minus alpha 1 V1 and minus alpha 2 V2 and minus, eventually minus alpha k vk. Okay, so far so good. There is no surprising. Now what I will do, since alpha is not equal to 0 by the assumption, I will divide by alpha 3. So no, divide by alpha 3, divide by alpha 3, and divide by alpha 3. But here's the problem. That means alpha 3 can be written as a linear combination of this vector, v1, v2, up to vk, except of course v3. So this means that the vector v3 is linearly dependent on the previous ones. And that's why we said the condition that must all these become 0. If all that becomes 0, we cannot divide by alpha 3, so they are independent of each other. This is why we define the notion of linearly independent as such. That if we have the linear combination is equal to 0, that means each constant or each coefficient must equal to 0. Otherwise, that means that one of the vectors can be written as a linear combination of the previous vectors. Okay, so this is the idea, or this is the notion of linearly independence. Example, we have these are the bases in R3. So we have the vector space is R3, and we have this vector 1, vector 2, vector 3 are linearly independent, and the span of them is equal to the whole space. Let's show that. So how we can show it's linearly independent? We apply the condition. We assume that the linear combination is 0 plus alpha 2 plus alpha 3 0, 1 is equal to 0. So from here, we must get all these alpha 1, alpha 2, alpha 3 equal to 0. Otherwise, that means they are linearly dependent. So we'll get alpha 1, I'm just subbing, so alpha 1 0 0 plus 0 alpha 2 0 plus 0 0 alpha 3, this is equal to 0. Of course, here when we write the 0, we mean the 0 vector. So actually it is 0 0 0 like this. Now we just sum. So alpha 1, alpha 2, alpha 3 is equal to 0 0 0, which means that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to 0. So indeed they are linearly independent. Now to show how, I don't have space to show that the span of them is equal to R3, but we can see it from here. So we can see it that if we have any vector, I will just write it quickly because most likely you are familiar with this concept. So the span is all the possible linear combination. So if I take all alpha, so alpha 1 v1 plus alpha 2 v2, etc. So eventually I will get something like this for any alpha 1, alpha 2, alpha 3 in R, but this actually it's the definition of R3. I hope it's clear. Unfortunately, I don't have the space, otherwise I will maybe explain it in the detail. Now we have the vector, it is C2, so it's a special case of Cn, and we have these two vectors, and show they are not linearly independent. So let's show that. So let alpha I 0 plus alpha 2 minus 1 0 equal to 0. So what I need to show that there is alpha 1 and alpha 2 such that they are not equal to 0, but they satisfy this equation. So by trial, we can see that if we take alpha 1 is equal to I, so take alpha 1 is equals to I, and alpha 2 is equals to 1, what we will get? I times I, this is equal to, sorry, take it minus I actually. So I times minus I will get 1 plus minus 1 is equal to 0. But as we can see, alpha 1 and alpha 2 are not 0. So these both vectors are not linearly not linearly independent. And also we can see that clearly because one can be written as a linear combination of the other. In particular, I0, for example, can be written as I times the other vector, which is, right? Let me check, minus I. Minus, yeah. So as we can see, they actually depend on each other. So they are not linearly independent. Now example 5, now we are dealing with the second most important vector space, which is the set of continuous function. We have this vector, which are vectors of this the vector space, which is 1x. Now here 1 we mean the function 1, x we mean the function x, up to x to the power n are linearly independent, but the vector space cannot be written as the span of this. I will explain the second part a while, but let me show that they are linearly independent. It's very simple. Let me take a linear combination. So alpha 1 plus alpha 2x plus alpha 3 alpha 1 alpha 3x squared up to alpha actually I need to call it alpha 0 better, like this, up to alpha n x to the power n is equal to 0. But we know from the polynomial identification, we know that alpha all these must equal to 0. So this is a very primitive example, equal to 0. Now why the span of this, so all of the possible linear combination are not possible to be equal to the vector space? Very simple. We have a vector which is the function of x to the power n plus 1, which is inside my vector space, which is all the set of continuous function from a to b, right? Because x to the power n plus 1 is a continuous function. However, it is impossible to rewrite it as a linear combination of polynomial to the power n, again by the polynomial identification. So x plus n cannot be written as a linear combination of xn. So we have a vector on my vector space which can't be written as a linear combination of these vectors. Then it's impossible to span all the space. So again, because what's the meaning of a span? That means that any vector can be any vector and v can be written as a linear combination of the span, or of the vectors in the span. Okay. Again, by the way, I'm explaining very fast because I'm assuming that all these notion and all these ideas you are already familiar with it. Now we define the notion of basis. So a set of vectors, so we have v1, v up to vk, called basis if they satisfy, for a vector space v, if they satisfy two conditions, only two. First of all, they are linearly independent, so they do not depend on each other. Second of all, they span v, so any vector in the vector space can be written as a linear combination of these bases. Now here's also just a reminder that the choice of the vectors of this vector, which the bases, are not unique. So the choice of the vectors which form a basis is not unique. However, the number of such vectors is unique and called the dimension. So now we define what's the dimension of a vector space. So a dimension of the vector space is unique, but the choice of the basis is not unique. For example, R3, the real numbers that we know, vectors, R3, we can choose a vector like 1, 0, 0, and 0, 1, 0, and 0, 0, 1. So this is a basis which has, we have three bases. Now we can change it. We can, for example, choose 2, 0, 0, 0, 1, 0, and 0, 0, 3. This is still a basis. So they are different bases. So it's totally unique to the choice of bases. But in all cases, we must have three bases. So that means R3 has a dimension of 3. Sometimes, as we will see in the continuous function, and the set of continuous function, we don't have a finite number of bases, so we call it an infinite dimensional vector space. So we take this example, C2. So we have two vectors, show they are bases. So what we need to show? We need to show two things. The first thing is that they are linearly independent. Clearly they are linearly independent, but let me show it very quickly. So 0, 0, I equal to 0. So this is immediately we can see that means that this must equal to 0. So this indeed linearly independent. Now we need to show that any vector in my vector space can be rewritten as a linear combination of v1 and v2. So let me take a specific vector, or arbitrary vector. So it will be something like this: alpha beta, where alpha beta are complex number. So this is the form of C2. Any vector has this form. However, I can rewrite it as the following: as alpha 1 0 plus let me see, or minus I beta, right? 0 I. Let me check if we distribute this here. So as we can see, it is alpha v1 minus I beta v2. So it's a linear combination. Any vector can be written as a linear combination of v1 and v2. Notice here c2 is over c, so we are allowed to use a scalar from complex scalar. If, and this is, I will just do it as assignment, if my space is over R, so the only allowed scalar that I can use are the real numbers, then the dimension will be actually 4 dimensions. Okay, but in most cases we'll deal with vector spaces which are over the complex number. So here that show that the set of continuous functions is infinite dimensional vector space. This is, and you can do it by tricky ways, considering the following set, which is this set: 1 x, يعني up to x and n x up to n, and then n plus 1 and so on. So as we can see, all these vectors are linearly independent, but the set of this can go to infinity. So it's not finite, right? We can take x to the power any n. There is no limit to take it. يعني for example, yeah, I can take for example 1 x to the power n. Okay, then I can take x n plus 1. X n plus 1 cannot be written as a linear combination of any of these. So I will add it here to this set. So let me add it. Then you can take n plus 2, which cannot be written as a linear combination of the previous, and etc. so forth, so on. So this set, which is infinite and it has infinite dimension, can't be written, and they are linearly independent. Thus, we have we have infinite bases. So it's possible to have a finite dimensional space, which are the continuous function. In general, this is a very well-known fact that we have to take it. Any vector space which consist of function, usually it's an infinite dimensional vector space. Not usually, always. Now we reach to the concept of inner product, which is a property still inside the vector space, or not. We are inside. We are not talking about the relation in between. So it's a mapping of a pair of vectors to a scalar. So basically, you have two vectors and you map them to a scalar. We can think of this as a generalization of the of the dot product that we are familiar with from high school. So now, what's the properties of this inner product? The first property, that the inner product with a vector with itself must equal to positive quantity, and it is equal to 0 if and only if the vector space, the vector itself is equal to 0. Okay. And in general, just saying, this is a quick remark. It is actually the norm of a vector. We call it the norm of a vector square. So we can define the norm of a vector as the square root of this quantity. Now we are sure that it is positive, so we can take the square root of it. Now, if we have an inner product of two vectors, and we have one vector which is multiplied by alpha, it must be the right vector. Be careful. So here the direction is important. So we can take this constant outside. So for example, just take a numerical example. if we have v1 and we have 5 of v2, so this can be written as 5 v1 v2. Okay, now this is also the linearity, so both the second and the third condition are called the linearity. So we can distribute the addition. So basically this is, we can think about it in terms of the dot product as the following. So if we take the dot of vector plus c, we can distribute it. Okay. The second, this one is crucial and important, and we will use it a lot, that it's not commute. That means that if we take the inner product v with respect to 2, and then you flip, you take 2 with respect to 1, and you start with 1, and you start with v1, and then v2, and then you decide to flip v2, v1, you must take the conjugate. We say that it could be, this result could be a complex number, so we can take the conjugate. It's very important, this property. In quantum mechanics, as I said previously, we have the vector, we call it the normal vector in the vector space, we call it a kit vector. While the vector, if we flip it, so on the right, on the left, right or the triangle on the left, we call it a bra. And we will show what is the bra vector for the corresponding kit vector, because it depends on the space. We will show it inshallah later. So we can denote the inner product as a product of the bra times the kit. So what we will have, and that's why we call it a bra and kit. Maybe it's first when you hear it, it seems strange, but then it will make sense. So the product, the inner product will becomes a bra kit. We have this as the C, so it will be a bracket. Now, as I said previously, in quantum mechanics, we will deal only with two Hilbert spaces, or two vector spaces. So we'll have the first vector space, it is Cn space, so the space of where you have a column of a complex number, and the second space, it is the continuous space. So let's discuss each space, what is the inner product, how we define the inner product, and how we define the bra vector. So let's assume that we have two vectors in our space Cn. Then each vector, as I said, we can represent it as a column of n complex number. So let me maybe write something here to make it clear. That ai and bi are all in the complex numbers. So the inner product between alpha and beta, or the bracket, or if you want to call it, it will be defined as such. Notice it is like the dot product between two vectors, but the only difference, the vectors on the vector on the left, we take the conjugate of it. This is a very important thing to note. So we take the conjugate of A times the first component, so we take the conjugate of this times this, conjugate of this times this, and we sum. It's exactly like the dot product, but with the difference that we are taking the conjugate of the vector on the left. So from here we can define what is the bra vector in Cn. So if you have this is the kit vector, right? So the bra vector, first of all, it will be a row vector. So here we have a column vector. Here will be a row vector, and we will take the conjugate of each component. So this is the definition of the bra vector in Cn. So as we can see, it's very simple, and it's very clear and very neat. So then we can define what is the inner product. It's the product of the bra vector times the kit vector. And indeed, if we notice, if we multiply this by this, we'll get back to the expression for, or the definition for the inner product. Now the second space, which is also important and we will deal with a lot, which is the continuous function. So how we define the inner product between two continuous function. So it's defined as such. So let's assume we have two vectors which are in the space of continuous function. Then the definition will be something like this. First of all, let me say something. This definition is not unique up to a constant. So we can multiply here by any constant. 1 over 2 pi, 1 over whatever a, some constant. So this definition is not unique, so we need to define it if you work in the space. This is just a technical thing. But in general, this is the definition for it. So you have the function on the left, you take the conjugate for it, times g, and then we integrate over the limits. The limits, of course, depends on the problem. So sometimes it's يعني مثل اليوم شفنا previously, sometimes we'll have from minus infinity to infinity. Other maybe we can take it from, for example, 0 to 2 pi. It depends. So these are the definition of the inner product in the different spaces. We have here for Cn, and here we have for the continuous function. Let's consider a specific example. Let's take a specific case for Cn, where n is here 2. So we have so we have vector of 2 components, where each component belongs to the complex number. So let's find now the inner product from v1 and v2. So what we do, we can write it as such. First of all, I will take the bra of v1. What's the bra of v1? I need to flip it 1, and I take the conjugate, so it is minus I. So this is the bra of v1 times the kit of v2, so it will be the same. That is it. Now if we multiply, so it is equal to I minus I, so it is equal to 0. Now if you notice, this must be equal exactly as if we do it in using the definition blindly. We take the conjugate of the first one times the first one, so 1 conjugate times I, this is times I, plus the conjugate of this, which is minus I. Be careful. So let me write it minus I conjugate plus 1, and this is indeed is equal to 0. Sorry about that. Now let's take the opposite. So let's take v2, v1. If we do it, we must get also 0. So it's minus I 1 1i. This is indeed equal to 0, which is equal to what? It is equal to 0 conjugate, because remember, v2 v1 must always equals to v1. I can flip them, but I need to take the conjugate. Okay, now we reach to a very important concept and notion that it is any borrowed or comes as a result after the inner product, which is the concept of orthogonality, which is very crucial and very important in the linear algebra in general. Just a small terminology. Orthogonal, actually it has 2 words, ortho and agonal. Ortho means something straight, and agonal means that the triangle, the angle itself, it is straight angle somehow. So we have something like this. So they are on the straight angle. So that's why we have, for example, the Orthodox. So with the Orthodox Church, what does that mean? That they follow in a straight line the Jesus Christ. And this is just information. And the orthogonality and the Orthodox Church, they comes from the same root of the word. عموما نرجع لموضوعنا. So as I said, defining the inner product in the vector space allows to define the notion of orthogonality. So if we do not have the inner product defined in our space, we cannot talk about the orthogonality. What's the hell the meaning of the orthogonality? So let's assume that we have 2 vectors. As usual, they are cut vectors. We say that the first vector, is orthogonal to the second vector if the inner product is equal to 0. As simple as that. Now, if you remember from your elementary mathematics, when you introduce to the concept of the dot product, we say that 2 vectors are orthogonal if the dot product is 0. This is, as I said, this generalization, because we define the concept of orthogonal, the concept of inner product to function. So we can discuss what does mean a function to be orthogonal to another one. Physically or geometrically does not make sense. We have function and another function. What's the meaning is that both are orthogonal to each other. But after we defining the inner product, okay, so it has a specific meaning. Generally, we say the set. So if we have many vectors, k vector is orthogonal. So is orthonormal So it's composed of two words, ortho and normal. So if we have these vectors are orthonormal set, if, and I believe we discussed this previously, if for different vectors, yani for example 1 and 2 they are orthogonal, but if they are the same we get 1. Okay, now here's a remark I want to write it. Not sure if I write it previously. It's the following: if you have the same vector, the inner product of same vector, so v1, we said that it's already positive, so this is actually, it's equal to the norm of the vector square. So basically from here, from this relation, we deduce that the norm square is 1, so the norm is 1, so the norm of the vector is 1. And that's why we said normal, orthonormal. So they are orthogonal and they are normalized. So let's consider the example of this vector spaces. I believe it's the same as the previous one, or very similar to it. So if we take the inner product with it, so if we take I conjugate 1 and minus I 1 is equal to 0. So these two vectors are orthogonal. Now, are they orthonormal set, or عفوا, is this the set is orthonormal? Let's check. Let's take specific vector, which is this vector. So we can take it as following. So it is I conjugate I. So that is equal to what? If we take, so it will be minus I, so it will be 1 plus 1. So it has a norm of, so this is the norm of the vector square. So the norm of the vector is square root of 2. So it is not orthonormal. Not or sorry, orthonormal, unfortunately. Okay, we can of course divide by 1 over square root of 2 and make it orthonormal. This is up to you. Now the next example, it is you have a continuous function from 0 to 2 pi, and we have these two vectors. So yeah, two vectors, which is sine theta and cosine theta. And this is very important in Fourier analysis. When you study it, you need to know the fact that sine and cosine, they are orthogonal functions. So let's show it. So the inner product, it will be from 0 to 2 pi. The first one conjugate, okay, and the second one is normal, d theta. Of course, it is equal to itself, so I will, and the conjugate of sine theta is the same as the sine theta. This is equals to half from 0 to 2 pi sine 2 theta, right? Then this is equals to 1 over, I believe, 4. Don't care, so it is cosine 2 theta with the minus sign. And this is from 0 to 2 pi, and this is equal to 0. So indeed, sine and cosine are orthogonal functions. Now, as I said, the notion of orthogonality is essential in linear algebra and in general in mathematics, the concept of orthogonality. Why is that? Basically, it's the following. Let's assume that you write a vector, specific v, in terms of a linear combination of orthonormal vectors. And that, for example, if you have a basis for R3, you have these bases 1, 0, 0, 0, 1, 0, and 0, 0, 0. These are orthonormal vectors, so we can rewrite any vector in terms of them. So let's assume we have a vector, specific vector, which can be written as a1, v1, a2, v2, until an, vn. Now this is, we call it the components of the vector. And if these, the vectors, the bases, for example, are orthonormal set, then the following is true. The components basically is equals to the inner product. Why is that? Let me show it. So if I want to show, to find, for example, a1, how can I do it? It's very simple. I will take the inner, I will multiply by the graph we want of a1. of V1, sorry. Okay, this is V. So this is basically the left hand side of the equation, of this equation, is equal to A1 is a constant. So let me write it slowly. So V1 inner product with A1 V1 plus V1 A2 V2 إلى آخره. Now this is A1 is a constant, and it is constant on the left, صح? عفوا, on the right, so we can take it outside. Let me show you the property. So we have it somewhere here, the property of the inner product. Yeah, so we have the property here. So if it is on the right, we can take it outside as it is. So if we take it, so we get A1 V1 plus A2 V1 V2 plus A3 V1 V3 and etc. But we know they are orthonormal sets, so this must equal to 1. So this is equal to A, I'll not write 1, plus. Now these are orthogonal, so V1 is orthogonal to V2, so it's equal to 0. And V1 is equal to V3, equal to 0. This by definition of orthonormal set. So this is the beauty of orthogonality. So if we have a basis which are orthonormal, then we can basically find the components, or in other words, we can rewrite the vector in terms of this. This is a very important identity that we use a lot in physics, which is that any vector eventually, if you have the basis, so let's assume this is, so V1 and V2 until Vn are basis for your vector space, then any vector can be written as V1. As I said, how to find the component is basically using this equation. So you write it as V1 and that product with vector. So this is just a scalar, يعني اللي هنا scalar V1 plus V2 and etc. Now why this equation is beautiful? Because you write your vector in terms of, totally in terms of your vector and in terms of the basis. So this is all what you need. So this is a beautiful and compact way to represent your vector, and we will use it. And I believe we already see this previously in the context of quantum mechanics, and these are familiar, but now we are familiarize it, or we put it in more rigorous context. Now this is an interesting example. Actually, it's even not an example, and we can use it as a important formula to find the magnitude of a vector square. So we know that this quantity, as we said previously, it is defined as the inner product of the vector with itself, right? So we can write it as the bra vector times the kit vector. But what is the kit vector? We have it previously here, صح؟ هذا هو. So we can write the kit vector as the following. So let me just write it here. Let me big bracket. I will write it in the red. So we can write it as V1 V, then V1 plus V2 V. So these are just the component, V2 and etc. Okay, so the whole thing, this is actually, it's what is the kit vector. Now if we distribute, what I will have the following. I will have V1, so V, let me write it in red. So هذا ال V1, so V1 V, then times V1, plus we can see a pattern, V2 V V2 and etc. But be careful that using the property of the the property of the inner product, we can interchange this. So we can write it as v1, and we can flip this in condition that what we put a star. So we take the conjugate for it. But what is this? This is basically, so let me just write it. So for example, this is for 2. So we can again flip plus da da da. Now, but what is this? So if we have a number and we multiply it by, let me just remind you, if we have a number, a specific number, our constant, and we multiply it by the conjugate for it. So this is equal to the norm of this constant squared. So in this case, this is equals to, this is, actually this is, I would call it A1, so the component, A1, so this is A1 star. So then this is equals to A1, the whole thing is squared, plus A2, and up to AN. So finally we get our formula, which is that the norm of a vector space square, it is A1 square, and this is the formula. Sorry. It's a very, very beautiful, and it's a normalized for the concept of the norm. So how we can use it? For example, if we have a vector, this vector, let me assume that is equal to 1 I 1, and I said find the norm. We can find the norm as previously. We take basically this quantity, and this is equal to the norm square. Or we can use this formula. So the norm of a vector square, it is basically the first component square plus the norm of the second component, which is 1. So the norm of I square plus the norm of the 1 square. So this is equals to 3. Thus, the norm of the vector is equals to square root of 3. We usually use this formula, and previously maybe in your and you counter this formula, but maybe you don't know what's the rigorous way to show that it is correct. And yeah, we finished from the part of the vector spaces. Inshallah, from the next video we'll start with the linear operator or the linear transformation.